Previously on Physicsball Z, our heroes discovered the different stores of energy and were able to correctly identify the definitions. They also encountered several transfers of energy, but just when they thought they had everything under control, they were attacked by this past paper question. However, through the power of highlights and the physics equation sheet, our heroes subdued and solved the values, finally calculating this monstrosity of a question. And now, our heroes have located the source of the up's power. Will our heroes be able to end this efficiently, or will the potential difference in their power be too great? Find out in today's episode of Physicsball Z. Here are the retrieval questions for this lesson. You know what to do. Specific heat capacity is the energy change over mass and temperature change. The specific heat capacity of water is 4,200 joules per kilogram Celsius. Arteries are blood vessels that take blood away from the heart. Veins are blood vessels that take blood to the heart. Graphite has delocalized electrons which are free to carry a current. Metals have delocalized electrons as well, which are also free to carry a current. We will be dealing with some large numbers, so spend some time matching up these prefixes. Micro is the smallest of these with 6 zeros in front of your first significant number. Kilo, as we should know, is 1,000. Milli is 1,000th of a meter, so there's 3 zeros in front. Mega is the largest of these and is 1,000,000. Now see if you can write these numbers in standard form. I've done the first one for you. When the decimal is before your significant number, you have a minus sign to indicate that it's a small number. The number afterwards shows how many decimal places you needed to move your decimal. Kilo is 1 times 10 to the power of 3. Notice that numbers larger than 1 do not have a minus. Mega is 1 times 10 to the power of 6. Micro is 1 times 10 to the minus 6. Again, notice that the decimal moves to the right when it is negative and it moves to the left if it's positive. Here I have Almighty and All for One. Have a go at these challenge questions. To turn a megajoule into a joule, we have to multiply it by 1,000,000. Therefore, 5 megajoules is 5 million joules. Turning kilojoules into joules, we need to multiply it by 1,000. Therefore, multiplying 4,500 kilojoules by 1,000 gives us 4.5 million joules. For the last question, it tells you that power is joules over second. That means that we have to divide the joules by the time we have, which is 2 seconds. This gives us 2.5 million joules per second for All Might and 2,250,000 joules per second for All for One. As we just saw, power looks like this. See if you can work out what the equation for power is. Power is energy over time, and the unit is technically joules over second, but we have a special name for this. It's called a watt. And here are 2 equation triangles that you need to not only memorize, but we'll also be using these shortly. The first one, we've got work done at the top. So work done equals power times time, but power will be work done divided by time. And the second one, which is the one you're probably going to use the most, is going to be power equals energy transferred, or energy divided by time. Here I have 4 different devices that use different amounts of energy each second. See if you can match up the power ratings below with the correct devices. The torch obviously uses the least number of joules per second and will be matched up with the lowest. The electric cooker will use more energy than the light bulb and less energy than a rocket, so it should be the second highest. That means that the bulb should be 100 watt and the rocket will be 100 megawatts. Please don't forget that this means joules per second. So a torch is giving out 1 joules of energy each second, but a rocket is giving out 100 million joules of energy each second. It is likely that you will have to convert one or more units in your exam. In this question, we need to calculate power when the energy is 10 kilojoules and the time is 1 minute. The equation is energy over time, but we need our energy in joules and our times in second. Kilo is 1,000, so we times the kilojoules by 1,000, and also we need to convert our minute into seconds. So 1 minute is 60 seconds. This gives us 10,000 joules over 60 seconds, which is 166.6 watts. Here's a past paper question similar to what we just did. To heat a house, the boiler transfers 15 megajoules of energy in 10 minutes. Calculate the power of the boiler. Write any equation that you use. First, we need to convert our units to joules and seconds. So that's 15,600,000. The equation is energy over time. Sub in the numbers, we get 15 million joules over 600 seconds, and this gives us 25,000 watts. This next question will require you to rearrange the equation. The table gives you information on 2 scooters, A and B, and you have the power and the mass of both. The question asks you to calculate the energy transferred by the motor in scooter B in 20 minutes. First, you should convert the minutes into seconds, then rearrange the equation, and that will give us energy equals power times time. Sub in our numbers, we get 700 times 1,200, which gives us 840,000 joules. This next question is technically in the electricity unit, but since you need to calculate power, I slipped it in here. Power can also be calculated by multiplying current and potential difference. This is what the equation triangle looks like for this. Power is on the apex, potential difference and current are on the bottom. Here's an opportunity to practice calculating the different components of this new equation. Do you think? The first question is asking us to calculate power. We simply need to multiply the potential difference by the current. This gives us 19.5 watts. The next one, you need to calculate potential difference. This is power over current. This gives us 0.87 volts when you round up to 2 decimal places. Finally, we need to calculate current, which would be power over potential difference, and that is 1.33 amps. So far we've seen these 3 equations. Power is work done over time, power is energy over time, and power is potential difference times current. But there is another. This is when you're given the current, but instead of potential difference, you're given the resistance. And this is what that looks like.
Oh my god.
I know it looks a little bit wild, but it's really not that bad. Power goes on top of our equation triangle. Current squared is at the bottom, along with resistance. This means that if you're asked to calculate the current from the resistance and the power, you will need to work out the square root of the power over the resistance. Alright then. Have a go at these challenge questions. Power is the current squared times the resistance. Subbing our numbers and squaring the current will lead to 250 watts. Resistance is the power over the current squared. Subbing our numbers and squaring the current will give us 111 ohms. Current squared is power over resistance. Subbing our numbers gives us 1000 over 10. We need to square root the right hand side to give us the value for the current. 1000 over 10 gives us 100, and therefore the answer there will be 10 amps. We've looked at all the power equations that you need to know. Now let's move on to efficiency. When I was your age, all the bulbs in my house looks like this. You probably have some energy efficient light bulbs around you now. But before we get ahead of ourselves, have a go at these challenge questions. The useful energy output is light energy. The temperature reading on the thermometer will increase if we put it near the light bulb. This tells us that some of that input energy is wasted as thermal energy. In other words, it's not 100% efficient at converting electrical energy into light energy. When heat energy is lost, we say that it has dissipated. This just means that it's gone into heat that can't be useful. Light bulb A is a traditional filament light bulb and B is a fluorescent light bulb. I've got these challenge questions for you to have a go at now. I'll give you a hint for the mega challenge. Efficiency is never greater than 1. Bulb A will feel warmer. The most efficient light bulb will be B. We can see it in the numbers. A converts 500 joules of energy into 50 joules of light, but B converts the same joules of energy into 400 joules of light. Since the efficiency is not greater than the input energy, you should have seen that the only way to calculate this that makes sense will be having the small number on top, which means that it will be the output energy or the useful energy that will go on top. This gives us 0.1 for bulb A and 0.8 for bulb B. The equation for efficiency is split into two depending on whether you're given energy or power. The first is useful energy output over the total energy input, and the second is useful power output over the total power input. Notice that for both, the useful output is over the total input. Let's look at some past paper questions for these. Figure 2 shows a food processor. The student places the cooked potato into the jug of the food processor. The food processor contains a motor that spins blades to chop the potato. The total power input in the motor is 500 watts. The useful power output of the motor is 300 watts. Calculate the efficiency of the motor in the food processor. Efficiency is useful power over total power input. This is 300 watts over 500 watts. This gives us an efficiency of 0.6. Here's another example. We have been given these values and we need to calculate the useful power output. When we put that into our equation, we get 0.15 equals useful energy over 3.2 kilowatts. Since we want our answer in kilowatt, we do not need to convert the watts. Rearranging that to give useful energy output gives 0.15 times 3.2 kilowatts. This gives us 0.48 kilowatts. The next one is a triplet of questions. The first is a bog standard efficiency calculation. The second is you calculating the power wasted. This should be pretty straightforward if you know the total power input and the useful energy or power output. The last one's got to do with what happens to that wasted energy. Do your thing. Efficiency is the useful over the total, so that gives us an efficiency of 0.9. Wasted energy will be your input take away your useful output, and this will be 60 megawatts. This wasted energy, as we saw, is dissipated, so the temperature of the surroundings will increase. This final question here is an interesting one. You need to calculate the efficiency of the motor in test D. We know that we need the input and the output, so these are the two columns we need to look at. Try and work this one out. Input is 80 and the output is 120. This means that it's 120 over 80. This gives us an efficiency of 1.5. There's clearly an error here in the measurement because efficiency, as we saw, cannot be over 1. And there we go. The mission is complete.
Fatality.
Check the descriptions to collect the goodies, use the timestamps to skip to wherever you need to go to, and I'll catch you guys in a bit.